Hey everyone. In this video, I'm going to start going over the solutions to the 2019 International Practice Exam. I'm actually going to split these problems up into their own videos so that I can keep the length down. So in this video, I'm just going to be going over the first question. The first question has 5 parts. The point values are all listed over to the side here. And in the first part, we are looking at a cart which is fixed in place on a horizontal surface and has a little projectile launcher at the back. And there's a projectile that's being launched with some speed v0 at some angle theta above the horizontal. We're told to ignore this little height here. We're told that that's negligible compared to any of the other distances involved here. So just assume that this is being launched from the ground and it's going to go through the air and land over here at point P. All right, so the first question we're given is to derive an expression for the time that it takes the projectile to reach this point P here. All right, so since we're ignoring this little positive vertical offset here, there is a symmetry in the motion. The object is going to have a certain initial vertical velocity, which is v0 sine theta, and it's going to have that same velocity but in the negative direction when it lands. So one way we can approach this is to say that the initial y velocity for this object is v0 sine theta. The final y velocity when it lands at point P is going to be minus v0 sine theta, and the acceleration in the y direction is going to be minus g. So we can make this a kinematics problem. By definition, the acceleration is equal to the change in velocity divided by time. So if we rearrange this, time is going to be Vy final minus Vy initial divided by the acceleration, or we get 2 V naught sine theta divided by g. Okay. Part B asks us to sketch the horizontal and vertical components of the velocity as a function of time, starting from when it's launched and ending when the projectile lands at point P. All right, so our axes look like this. So the thing to know here is that the horizontal and vertical motions are independent. In the horizontal direction, there is no acceleration because there's no force, so we are just going to have a constant horizontal velocity the entire time. In the vertical direction, we start with a positive velocity. We're going to end with a negative velocity of the same magnitude at TP, and then halfway through, the velocity is going to become 0. So our velocity graph looks like this. All right, so we're asked to explicitly label the vertical intercepts here with algebraic expressions, and that just comes from trigonometry. The initial speed is v0, so in the x direction we get v0 cosine theta, in the y direction we get v0 sine theta. Okay, so in part C, we're going to modify our setup a little bit. All right, so in part C we are going to free up this cart to move horizontally, and in fact we're going to give it a horizontal velocity v1 moving to the right as this projectile is launched. So when this projectile is launched, now instead of landing at point P, it is going to end up falling short and land over here at point Q. Okay, so our first question for this new scenario is to give a physical reason why the projectile lands at point Q instead of point P or somewhere else. All right, so what is going on here? Why does the projectile not still land at point P? So the idea here is that the velocity of this projectile is a combination of two motions. It's moving with the cart, so before it is launched, its velocity is not 0 in this case, but it has a velocity of v1 in this direction. So you can say that the projectile has horizontal velocity at the moment it is launched. and that horizontal velocity is in the rightward direction. So its velocity with respect to the ground is going to be its velocity with respect to the cart plus the velocity of the cart with respect to the ground. So the velocity of the projectile relative to ground is going to equal v0 cosine theta, that's its launch velocity with respect to the cart, minus the velocity of the cart with respect to the ground. So I'm treating sort of forward, so to speak, as the positive direction here. So we used a positive velocity in the last section, so I'll be consistent with that and call the velocity of the cart negative. So as long as you are subtracting these two values, you should be fine there. All right, D, we need to get a little more quantitative. So we want to derive an expression for V1 in terms of the launch velocity and angle of the projectile and this distance d that it travels. All right, so the trick here is going to be to not try to immediately write an equation for V1, but we'll just write an equation of motion for the ball that's going to have V1 appear somewhere in it, and then we'll rearrange that. All right, so we have this expression in part C. This is the velocity of the ball relative to the ground the moment it's fired. Now, nothing has changed in the vertical direction, so the time of flight is still going to be the same. It's going to be 2v0 sine theta divided by g, and then the horizontal velocity is going to be this v0 cosine theta minus v1, and that horizontal velocity is going to be constant throughout the entire flight. So the motion in the horizontal direction is simply given by the horizontal velocity multiplied by the time. So d is equal to v naught cosine theta minus v1 times 2 v naught sine theta over g. All right, so we have to rearrange this. So first, let's just move everything that's out to the right of the parentheses over to the left-hand side of the equation. So we get gd divided by 2 v naught sine theta equals v naught cosine theta minus v1. So I'll add v1 to both sides and then subtract this fraction on the left, just move things around. I get v1 equals v0 cosine theta minus gd over 2 v0 sine theta. All right, so that's my answer for part D. All right, part E is where we finally start to introduce some calculus into this problem. So this is where things get a little bit challenging. Okay, so now we're saying forget everything about the projectile. We're just going to focus on the cart now. So after the launch, the cart's speed is v2, and then it experiences a braking force equal to minus b times v. All right, so here's our cart. So the initial velocity is equal to v2, and then there is a backwards braking force equal to minus bv. So this constant b has units, we're told, of kilograms per second. That's just required for this equation here to make physical sense. We have to have the same units on both sides of this equation here. All right, so that was just kind of a little side note. So for part one, we want to use Newton's second law to write a differential equation that represents the motion of the cart. So a differential equation is just any equation that has a derivative in it somewhere. So all we really need to do here is write an equation based on Newton's second law. Force equals mass times acceleration. The force is equal to minus b times velocity. That equals mass times acceleration. So the way we turn this into a differential equation is we simply write for the acceleration dv dt. So acceleration is the derivative of velocity with respect to time. So this is a differential equation because I have some function v in this equation and its derivative. All right, so I'm not solving this just yet for part one, but for part two, we are going to verify a solution to this. All right, so I'm actually going to solve this without assuming that I've been given the solution in the problem. So the way I would do that is first I'm going to do something called separation of variables. So move all of the v terms to the side of the equation with dv, and then move dt and any other terms involving t over to the same side of the equation. So when I do that, rearrange things, it should look like this. Right? So v only appears on the right side of the equation, t only appears on the left. So now what we can do here is put an integral sign in front of both of these. All right, so I have integrals for both of these. I actually want to find v as a function of time. So the way I'm going to do this is I'm going to integrate this from 0 to some arbitrary time t. On the right-hand side, I need the limits of this integral to correspond to the limits of the other integral. So when t is 0, v is just equal to, call it v of 0, and here v will be equal to v of t. So now when I do these integrals, the integral on the left-hand side is just a constant, so that's going to equal b times t, evaluated from 0 to t. Your calculus teachers might get a little mad about what I'm doing with these variables of integration, but I'll just sort of ignore that. On the right-hand side, I have m times the integral of 1 over v dv. The integral of 1 over some variable is the natural log. So it's going to be the natural log of v evaluated from v0 to vt. Okay, so now I put in the limits of my integral. On the left-hand side, I'm going to have minus bt minus 0. And on the right-hand side, I'm going to have m times the log of v of t minus m times the log of v0. Okay, so we can use the properties of logs here. Log of a minus log of b, remember, equals the log of a over b. So I'll use that to simplify the right-hand side a little bit. And then the left-hand side is just minus bt. All right, so now this is really just an algebra problem. We get the natural log by itself, and then we exponentiate both sides. So that's going to give us e to the minus bt over m equals vt divided by v0. And then finally, vt will be equal to v of 0 times e to the minus bt divided by m. This v of 0, that's just the velocity at time 0. We're actually told that that is what we're calling v2, so I can make that substitution. All right, so that is the answer that we get for part 2. That matches the solution we were given, so we can be satisfied that we've done this correctly. Another thing we could do is, since we're given a solution and asked to verify it, you could just take this equation here and plug it in to this original differential equation. If you're comfortable with taking the derivative of an exponential function, you should get the same answer that way as well. All right, so we have one last part here. Part 3 asks us to find an expression for the distance the cart travels from time 0 until the time it comes to a stop. So first of all, if we look at the equation we have here for the velocity, when does this equal 0? An exponential function actually has an asymptote. So if we plotted this, the velocity would start at v2 and then it would asymptotically approach 0. So technically, if we take this equation fully at face value, vt equals 0 only when t equals infinity. So we're going to find the distance by integrating the velocity over time. And we're going to go from t equals 0 to t equals infinity. All right, so we are integrating this expression v2 times e to the minus bt over m. All right, so the way we integrate an exponential function is we basically divide by the coefficient that is up in the exponent. That coefficient is minus b over m. So we're going to divide by minus b over m, which is equivalent to multiplying by minus m over b. So this is what we get when we integrate that expression, and we're evaluating that from t equals 0 to t equals infinity. All right, so when I plug in t equals infinity to this expression, I get 0 because the exponential term goes to 0, and then I'm going to subtract what I get when I plug in t equals 0. When I plug in t equals 0, the exponential term here is just equal to 1. So this is minus v2 times m over b. So this actually simplifies to a pretty nice expression, v2 times m divided by b, and that is the distance that this thing travels. If you want to check the units, remember b has units of kilograms per second, so m divided by b actually has units of seconds, so velocity multiplied by something with units of seconds gives you a distance.